Okay, so what imaging technique best describes time of flight MRA? It's a T1 technique because remember, we're using multiple shortly spaced 90-degree RF pulses. That's the critical thing I want you to remember. Short TR is going to give you T1 contrast. It's a gradient echo sequence because the spin echo sequence would do the opposite of what we want. It would boost signal from the stationary tissue. We want to suppress signal from the stationary tissue, and we want bright signal in the arteries. And spin echo is associated with dark signal in the arteries. So it can't be a T1 spin echo. It's going to be a T1 gradient echo. And then because it's a T1 weighted image, it's going to be susceptible to issues of T1 shine through, like we showed here in this example of dependent proteinaceous fluid in the left sphenoid sinus. Not an aneurysm. That's T1 shine through. Okay, so let's select the aneurysm. So this is not an aneurysm. This is CSF flow in the third ventricle. So again, this is the time of flight MRA. This is the T1 pre-contrast image. We know that this is the time of flight MRA because we see bright signal in the arteries and the stationary tissues are basically suppressed, okay? So we're talking about this right here. So is that an aneurysm? So we see this, hyperintensity on time of flight MRA in the third ventricle. So the first thing we want to ask, maybe there's a lesion there. So let's look on the T1. Is that T1 shine through? No, it's not. There's nothing in the third ventricle here. These are the thalami. The third ventricle is in between the thalami, right? So it's some kind of flow. So this is just CSF flow. So question, what direction is that CSF flowing? So it has to be flowing cranially, right? Because remember, in time of flight MRA, we apply that suppression pulse, saturation pulse, to the volume above where we're imaging. That's how we suppress the veins. So that means that this has to be coming from below, because if it was coming from above, it would have been suppressed. So this is cranially directed CSF flow. Pretty cool that we can tell that, right? All right, so these are examples of intraparenchymal hemorrhage, and you can get T1 shine through from this because the met hemoglobin and the subacute stage of hemorrhage can shorten T1. And so this one is particularly scary. I would think, oh man, is that an aneurysm? Again, this is a time of flight MRA because the arteries are white and the background tissue is relatively dark. It's not a T1 post-contrast. Remember, T1 post-contrast, you'd see enhancement in the dural venous sinuses, in the cortical veins, in the nose, in the choroid plexus. This is just very washed out signal in the stationary tissues and very bright signal in the arteries. So that's classic for time of flight MRA. Okay, that's how you recognize it. This is the T1 pre-contrast, the nose, right? There's no enhancement there. And we see that it's bright on the pre-contrast T1. So this is just a hematoma. This is not an aneurysm. Same thing with this. This is a hematoma, not an aneurysm, because it's bright on the pre-contrast T1. Okay, so I'll take this case. This was a partially thrombosed aneurysm. So we have an axial CT in the arterial phase, T1 pre, T1 post, T2 spin echo, and a time of flight MRA. On the non-contrast CT, we see this lobulated hyperdensity, ovoid hyperdensity centered in the left anterior temporal lobe. On the CTA, we see that the posterior part of it does fill in with contrast. So on the arterial phase, there is contrast in it. So we're wondering, is that an artery? Is this like a meningioma? It's not just a hemorrhage, right? A hemorrhage wouldn't enhance that solidly like that typically. So we're thinking, probably an aneurysm, right? Because it's enhancing on the arterial phase. So let's go to the MRI. So on the MRI, let's start with the T2 spin echo sequence. We know it's a spin echo because we see these flow voids. This is the horizontal cavernous internal carotid artery. Here's the basilar artery. So whenever we see black signal in arteries, it's usually going to be a spin echo sequence. And it's a T2 because the white matter is dark relative to the gray matter, CSF is bright, etc. So T2 spin echo, we see this black signal in the back of this ovoid thing we were talking about. That's really concerning. That could be flow, right? We want to make sure that's not like a flow void, right? So we're going to go to the time of flight MRA, and sure enough, there is bright signal on the time of flight MRA. So that is concerning for cranially directed flow, like arterial flow. So we're going to make sure that that's not T1 shine through. We're going to go to the T1 pre, and sure enough, there is no bright signal on the T1 pre. It's actually dark. So this is cranially directed flow, and that confirms that this is an aneurysm. If this was a meningioma, I wouldn't expect to see cranially directed flow. So it wouldn't be bright like that on the MRA. It would enhance on the post-contrast because that's just soaking up the gadolinium. But this tells us that it's actually an aneurysm by looking at the time of flight MRA and seeing that it's bright here and then it's dark on the pre-contrast T1. Honestly, we could tell on the CT as well. Whenever you see a round or ovoid lesion that's near an artery, you always want to ask yourself, could it be an aneurysm? So this is what an aneurysm looks like on the different MRI sequences and the CT. Okay, why is the left vertebral artery not visualized on the time of flight MRA? So this is an excellent case to review the principles we were talking about. So this is subclavian steal. So the post-contrast CT arterial phase shows a significant narrowing of the left subclavian artery. So this is the long axis view, and we see that there's this atherosclerotic plaque here. And if we look on the short axis, we see it's significantly narrowing the lumen. Look, that's the size of the lumen relative to the size of the artery. So significant narrowing. That means that the patient may reverse flow in their vertebral artery to bypass this stenosis. That's what subclavian steal is. So if we look at the post-contrast MRA, which is done in a similar way to a post-contrast CT, in that it's essentially timed to image when the gadolinium is in the arteries. You can think of it that way for now. So we see the common carotid arteries, both sides, that makes sense. And we see the vertebral arteries on both sides. So the vertebral arteries are open. But then when we go to the time of flight MRA, we don't see the left vertebral artery. So what's going on? So time of flight MRA applies a saturation pulse to the volume above the slice where it's imaging. As a result, anything that's flowing downward caudally into the slice is going to get suppressed. So usually that's going to suppress the veins because the veins flow from the head to the heart. But in a subclavian steal, that's going to actually suppress signal from the vertebral artery that's flowing downward, right? The reversed flow in the vertebral artery is going to be beginning above the slice where we're imaging. So that's what's happening. The time of flight MRA is suppressing signal from the reversed flow in the vertebral artery due to the subclavian steal, right? So with this absent flow could have also been due to a stenosis or an occlusion, but if that was the case, we would have seen that on the post-contrast MRA. So this combination of the time of flight MRA plus the post-contrast MRA diagnoses the subclavian steal.